Hey, Niklas, can you hear us? Nothing? Okay, great. Today I have a wearable microphone, so let's see if today it goes smoothly. So a couple of minutes more and we start the lesson. So let's start our second lesson on performance modeling and evaluation. Last Wednesday, you saw how to create queuing networks, which is a performance model. But you didn't see how to evaluate the network, so how to get the performance results. So the response time, the utilization, this is something that we will see in the next lesson using tools. Today we are going to see how to get some performance indices using operational loads. So we will be based on the queuing network model, and we will apply some operational loads. So in the first part of the lesson, I will explain these operational loads, and the second part we will do some exercises. If you are connected to Slack, and you see some message or some question from people online, you can notify me, because I have it open, but I'm not looking at this continuously. So today we will see operational laws, and these operational laws are simple equations which may be used as an abstract representation of the average behavior of almost any system. So the remaining three bullets specify the first one. So these laws are very general and make almost no assumptions about the behavior of the random variables. So they can be used in many systems. They don't need the particularities of the system. Another advantage of these laws is their simplicity. They can be applied quickly, so you will see that they are very short equations, and by almost anyone, because they are based on observable variables. So these observable variables are values which we can derive from watching the system, observing how the system works over a period of time. We can get the values of the variables that we will use for the operational laws. What we can observe. We have a system where requests arrive and serve the request, jobs, and then they will leave. In every example we are seeing here, we are not losing any request. So everything that comes in will circulate in the system, will execute, and in the end, it will go out. So we are not, requests are not disappearing inside the system. Everything that comes in will eventually go out. So if we observe this abstract system, we might measure some quantities, like 5 quantities. T, the amount of time we're observing the system. So T from time. A, the number of arrivals, the number of requests that arrive to the system. C, the number of completions, number of jobs that complete. Since we are not losing jobs, these two will be the same. B, from busy, the total amount of time during which the system is busy. The rest of time is idle. So the busy time will be lower or equal than the total time. And N, from the number of jobs inside the system. Okay? 5 easy quantities. Then on Wednesday, we saw that we can make a system made of subsystems. So this, what here is a system for us, it could be a part of a bigger system. So a system is made of subsystems like we saw this example last Wednesday. So we have the world system, and it has 4 subsystems. Request arrive to the left subsystem, and it could go to the upper subsystem, or down. From up, it could go to the right or to the first one again. From the subsystem down, it could go only to the right. From the right one, it could come here. So possible behavior of the job is coming here, going here, coming back here again, execute it here again, go here, come back here, again here, and complete it. So the job is circulating among traversing subsystems. So we can measure some quantities also at the subsystem level. We are going to use the same characters and with sub-index for the concrete subsystem we are measuring. So subsystem 1, 2, 3, 4, so we will have A sub 1, A sub 2, A sub 3, generically A sub k. So what we can measure at the level of subsystems, T, Okay? The amount of time we are observing the system. This is the same for every subsystem, so we don't use the subindex. A, the amount of request arrivals to the subsystem. C sub k, the number of completions we observe in the subsystem K. B, again, the busy time, so the amount of time that the resource, the subsystem was busy. Again, this at most, B is as high as T if the subsystem was busy all the time. And N, the average amount of jobs in the concrete subsystem K. Okay? Reasonable. You see how they can be measured. This was the same queuing network we saw last Wednesday when we represented this subsystem. So again, from the left, we can go to up or down. So from the first one, we can go up or down. From the upper one, we can go to the right one or to the first one. So when we finish in the up one, we can go to the last one or come back to the first one. So this queuing network represents the same behavior. So using these quantities that we can measure, we can directly derive some formula, some quantity. Right? These are in red, which is what we can directly compute. And every time during the rest of the slides that you see an equation in red, it will be one of these. Okay? So the first one, the amount of arrivals divided by the amount of time we have measured the system, we can compute the arrival rate. So the frequency with which arrivals arrive to the system. If we have counted the amount of completions and we divide by the amount of time we have observed the system, we can compute the completion rate, how frequently we complete requests, which is the throughput. If we have measured the amount of time that the resource is busy and we divide by the total amount of time, we will get the utilization, so the proportion of time that the system was busy. U. Busy time divided by the total time. If we have measured the amount of time that the system is busy and we divide by how many jobs we were able to execute, we can get the mean amount of time that each job required. So if the system we have observed the system for 20 seconds, 10 of which it was busy, and we were able, when it was busy, it completed 5 jobs. So if in 10 seconds it completed 5 jobs, means that each job required 2 seconds to complete. And if we know the number of completions in each subsystem, and we divide by the number of completions of the full system, we can obtain the average number of visits to the subsystem. So when a job arrives, how many times in average has to execute in a subsystem before it leaves. Any question with this? No? Clear? Okay. So an example of this. We have the same system as before, and we are observing this center. and we have observed this. So we have been for looking at the system for 26 seconds, from 0 to 26. And we have seen that during the first second, nothing happening. In the second second, a job arrived. During the third and fourth, the job was there and nothing happening. Second number 4, another job came. During 4 and 5, there were 2 jobs. At second number 5, one of the jobs finished it. So we had again 1. You understand how this? So we have been observing the system 26 seconds. The number of arrivals, yeah, 1, 2, 3, 4, 5, 6, and 7. The number of completions, the jobs are completed, also 7, 1, 2, 3, 4, 5, 6, and 7. And the busy time is 20. What? How it is computed?
The work time with 2 to 6 or here?
The amount of seconds that is not 0.
Okay.
So when it was doing something. So here it does not count, and so from 2 to 4, 2 seconds, plus 2 seconds, 4, plus 1 second, 5, plus 1 second, 6, plus 2 seconds, 8, plus 2 seconds, 10, plus 2 seconds, 12, 14, 16, 18, 20. So and the remaining ones, the system was idle, so there were not jobs. In these 2 seconds, there were not jobs. In these 2 seconds, there were not jobs. And in these 2 seconds, there were not jobs. So during 6 seconds, the system was idle. And during 20 seconds, the system was busy. So the frequency of arrivals to this research was the number of arrivals divided by the amount of time we have observed the system. So 7 divided by 26 requests per second. The throughput, the same. How many jobs were completed? 7 divided by the amount of time we have observed the system. The utilization, we observed the system during 26 seconds, and it was busy during 20. So 20 divided by 26. And the average service time, we had the system working for 20 seconds, so which was when it was busy. And during these 20 seconds, it was able to complete 7 jobs. So each job required, in average, 20 divided by 7 service time required by a job. Last lesson, we said that in the queuing network, we use the letter mu for service rate. And the inverse was the service time. It seems that?
It looks like the same number of arrivals and
Yeah.
completions.
Yeah. In the examples we will see today and the examples you will see during this course, it will be the same. Because we don't miss, we don't lose jobs. So a job will arrive and eventually it will, we produce it. So we are not, jobs are not disappearing in the middle, in the kind of systems we are seeing in this course. So this is the general theory. For us, the arrivals and completions will be the same. Good question. So let's start with the first law, utilization law. I think I used it as an example last Wednesday. Now we are going to see the definition. So the utilization of a resource is the throughput, x, of this resource multiplied by the service time of this resource. Let's see. Let's prove that this is true.
Average service time or
Hmm?
SK is
Yeah.
average?
Yeah, average service time, average throughput, average utilization. Everything is in average. Yeah. So we saw, here you have the, again, red formula, that they are the ones we saw before. So we have observed that the amount of time that the system was busy, and we divide by the amount of time we have observed the system, we get the utilization, the proportion of the system was used. So this one we knew already, so let's use this. The utilization is the busy time divided by the amount of time, the total amount of time. The utilization is equal to the busy time divided by the total time. Now we can multiply and divide by the same number here. So let's say that we multiply by the number of completions here and the number of completions here. This is still true, right? Now we can get we saw that the throughput of the system, the throughput of as a part of the system is the number of completions that we observed in this part of the system divided by the amount of time. So the number of completions divided by the amount of time is the throughput, which is x sub k. And we saw as well that the amount of time we observed that the system was busy divided by the number of completions was the service time. So if the system was busy during 10 seconds and it produced 5 jobs, the service time of each job was 2. So we applied this rule as well, and we have here the B divided by C. So we can put the SK. So we have the utilization is equal to the throughput multiplied by the service time. Okay. Example, a server K completes 40 requests each second, and each request requires 20 milliseconds. What is the utilization?
0.8.
0.8. So throughput 40, service time 0.02, 80% of time busy. Last Wednesday we saw that a service center could have one resource, one server, 6 servers, or infinite one. So this formula is valid for 1. If we have 6 servers, we divide by the number of servers. So to get the utilization, a number between 0 and 1, between 0% and 100%. An example of this, we have seen that a gas station serves 4 cars per each minute. So they are departing for 4 cars. And it has 5 pumps. And each car, we have seen that it needs 45 seconds for filling the tank and pay and leave. So the utilization of the gas station 4 multiplied by 0.75, so minutes and seconds. We have to put it in the same units. So we compute how many cars per second, or we transform the 45 seconds to minutes, which would be 0.75. So 4 cars, the throughput, 0.75, which is 45 seconds divided by 60 seconds in a minute, divided by the amount of resources we have. So this is our gas station is used 60% of time, 0.6. Next law, service demand. The demand is the total time a job is receiving service from a given server. Because the demand, we have not defined this before. So do not confuse this with the service time. The service the demand is defined by the amount of time the server was busy divided by the number of completions of the system, not of that resource. C, not C sub k. So if we see that the system is producing a completion every second, and our resource was busy half of the time, 0.5 seconds, the demand will be 0.5. So its request needs to execute 0.5. But we may have a service time of 0.1. So it means that the job had to execute 5 times in that center. So we had this. At some point it comes in. So at some point they will depart the system. And something happens here that it comes back. So if here we are seeing that it goes 1 request per second, and that this is busy half of the time, 0.5 seconds, the demand of each job will be 0.5 seconds. And on the other hand, so the demand. If we know that the service time of this is 0.1, that it can serve a job in 100 milliseconds, it means that we have done 5 executions here before leaving. So actually, this is the first relation. So the demand comes from the amount of the relation between the time the system was busy divided by the number of the amount of time the subsystem was busy divided by the amount of time that the system, by the number of completions that the system produced. This is how we define, and then we can reach these 2 laws. So we start with the second because this is the one that I mainly derive. If we have this definition, and before we saw that the service time is the amount of time that the center was busy divided by the number of completions in that center, we can substitute this bk but by the multiplication of S and C. So this changes to sk ck, and we are still dividing by c. Now we know that the number of visits to a resource can be computed as the number of the jobs that completed in that resource divided by the number of jobs that completed in the system, ck divided by c, and we have here a ck divided by c. So we can say that from this is the number of visits, and we have that the demand is equal to the service time in the resource multiplied by the number of visits to that resource. And we can also see the demand as the utilization of the resource divided by the throughput of the system. How do we reach this? We start from the same equation, and now we are going to multiply and divide by the same number. And now this number is the amount of time we have observed the system. Now the trick is done with the time. And we have defined that the throughput of the system is the number of completions we have seen, the number of jobs that completed at the system level, divided by the amount of time. And we have it here, the inverse. So will be something, and here the throughput. And we saw that the utilization of the system is the busy time divided by the amount of time. And we have it here. Busy time divided by the amount of time. This is the utilization. So, service demand law, we can compute the demand without knowing the blocking time or completions, but using if we know the utilization and the throughput. Okay? So an example, a server completes 2 requests every second, and the disk is used the 80% of time. What is the disk demand of a request? 40%. 40%? Yeah. Okay. So I have both results here. So we know the utilization, we know the throughput. Utilization is 80%, the throughput 2. So the demand 0.4 seconds. You say 40%? Okay. Seconds. The demand is in seconds. Okay. After I heard the 40, I was fine with that. So each request will use the disk for 0.4 seconds. So if we know that an execution of the disk service takes 100 milliseconds, how many times this request, have to access the disk? You have this demand. We divide by the service time, which is the 100 milliseconds, and we get the number of visits. So now it's using this part of the law to calculate how many times, the number of visits to the disk.
In a system, we must make sure that that request goes to that subsystem. For example, these 2 requests might not go to, might not need disk.
Yeah.
So, I mean, on the right-hand side we have K, and on the left-hand side we have K, DK and UK, right?
Where? Sorry.
In the equation, the main equation.
Yeah, okay.
EK and UK.
Yeah.
But how do we know that that two requests have gone through the disk? Because it must be, it might go through other services, other
Yeah.
subsystem than disk.
Yeah. So, because they are,
I don't know if I'm
Yeah.
clear or not.
I think so. So I'm going to answer what the question I understood. You mean there are requests that come and they may go to our disk or they can do something else. Yeah. And here we are observing 2 per second. And we are observing that the disk is at 80% of utilization. The disk demand, the average of each request is still 0.4. What does it mean? That some of them require 0 and some of them require more. But in average, each job requires 0.4.
We don't care about individuals' requests.
We will
About
care,
the average.
we can care when we know more tools to compute. Now these are simple equations and we are progressing on the power of what we can evaluate. With these laws, we can compute the average values. So we can say that in average, each request will use 0.4. And if we say that is like only the mu is 10, it means that we should have some cycle here as well. Yeah, some of them will use 0, some of them will use more than this 0.4, and in average, we have this 0.4. Next law. We showed this also on Wednesday as an example. Now we are going to prove that this is true. Little's law from John Little. The average number of jobs in a system is equal to the departure rate, completion rate, throughput, multiplied times the average time jobs are in the system, the residence time. We made the example with the supermarket. We see people leaving every 2 minutes. We are on the door. We don't know how many people are inside. We cannot look at this. But we see that people are leaving every 2 minutes. And we see that a concrete person, we measure the time that is inside till that person leaves. And we see that is 10 minutes in average. We can compute how many people are inside the shop or the restaurant. Okay, this is the law. Now let's use the equations we have seen so far to prove that this is true. So let's start with defining the W, which is we define it as the accumulated time in the system. Jobs per second, not divided by second. Job second. What does it mean? This is the same example we saw in the beginning. So 26 seconds and 7 completions, 7 arrivals.
The surface of the diagram.
Yeah?
The surface of
Yes.
the diagram.
So here it's a bit difficult to make the integral, so we are going to do the sum. So when there are 0, it adds 0. So 0 plus 0. Here there is 1 job, so during this second it counts as 1. So 0 plus 1 plus 1. Then there is another job, so during this second we count as 2. Because during second 4 and 5 we have 2 jobs executing in the system. So the accumulated time during this second, 2 jobs, counted like I'm waiting for a second here and the other one as well. So will be 0 plus 0 plus 1 plus 1 plus 2 plus 1, 1 plus 0, 0, 1, so the sum. So here there are 9 elements with value 1, 6 with 2, 1, 2, 3, 4, 5, 6, and 5 with value 3. So 1, 2, 3, 4, 5. So the accumulated time in the system by all jobs is 36 here, which is the area below the. The average number of jobs in the system is the amount of the accumulated time divided by the time we observe it. So we, like, if we do the average of this, of this line. So it's the 36 divided by the 26 amount of times we observe it. So we have this in average. Sometimes there are 0, sometimes there is 1, sometimes there are 2, sometimes there are 3, and in average we should reach 36 divided by 26, so 1 point something. And R is, we define now, like the average system residence time for each job. So how much time each job was in the system. We see that the sum of all jobs that were in the system, the accumulated time, 36. And we had 7 jobs, so the average time for each job, 36 divided by 7. Maybe some jobs were less time and some jobs were more time. So for instance, when 3 arrive almost at the same time, maybe some of them are waiting until they can execute, so they are more time in the system. But in average, this, 36 divided by 7. So we have these 3 values from observing the system. They are true. We also know, we have seen before, that the throughput of the system is the number of completed jobs divided by the amount of time we have observed the system. So now let's derive the little flow. Number of jobs in the system, amount, the accumulated time, waiting time divided by t, because it's this. So we saw that this is true by observing the system. Now we do a trick and we multiply and divide by the same value. So now we use the value c. We know that the throughput is the amount of completions divided by t, which is, here we have a c divided by t. So we can write the throughput, and it remains the w divided by c, which is what we call the system residence time. So we got that the mean number of elements, mean number of jobs in the system, the throughput times the residence time, which is little slow. So we saw that the mean number of jobs using this observation, so if we know the w and the t, was 36 divided by 26. Now if we don't know the w or t, but we know the throughput and the response time, which is, the throughput is the number of completions 7 and time 26, so 7 divided by 26. And the response time, which is 36 divided by 7, we obtain the, so using these 2 values, we obtain the 36 divided by 26, which is the same as. Clear? Okay. Next flow, the forced flow. The forced flow law shows relationships between the throughput of different components in the system And it says that the throughputs, also called flows, in all parts of the system are proportional to one another. And the proportion is the number of visits to the subsystem. So the throughput of the k resource is equal to the product of the throughput of the system and the visit count of that resource. The throughput of a resource, the visit count multiplied by the throughput of the system. Let's derive this. The throughput, we knew from before, right, that the throughput of a resource is the number of requests that completed that resource divided by the amount of time we have observed it. So throughput, completion divided by time. We know that the number of completions in a resource, so the visit, the amount of visits to a resource is the number, we can compute it as the number of jobs that completed in that resource divided by the number of jobs that completed in the whole system. So this C, we can move it here. So Vk multiplied by C equal to Ck. So we substitute this here and we get the other part, Vk multiplied by C. And we know that the throughput is the number of completions in the system divided by the time, which is this. So we get that the throughput at the element k is equal to the number of visits to this element k multiplied by the throughput of the system. So if a server completes 2 requests every second and each job requires 4 visits to the disk, what is the throughput of the disk? 8. 4 times 2. Another example, a car factory. We know that to produce, there are 2 robots, one for the doors, another for the windows. We know that to produce a car, the robot of the windows have to actuate 6 times. So 4 windows in the doors, 1 in the front and 1 rear. And the robot for the windows, for the doors, have to actuate 4 times, put each of the 4 doors. We have observed that the robot that puts the windows is putting 120 windows in an hour. What is the throughput of the robot that puts the doors? Still think about the solution. I'm not going to write it. I'm not writing the solution. So we apply it 2 times. The forced flow law. Do you have any number? People online have the number, the solution?
So the throughput is for an hour or for a second?
80. 18, 80. 80, yeah. Using the forced flow law, the throughput of the robot that puts the windows is equal to the number of visits to the robot that puts the windows multiplied by the throughput of the system. And the throughput of the robot that puts the doors is equal to the number of visits to the robot that puts the door multiplied by the throughput of the system. So to do it in once, you create the throughput of the system, the doors divided by the throughput of the doors divided by the number of visits, and you substitute it here. Doing it in 2 steps, we can get that the throughput of the system is the throughput of the windows divided by the number of visits. And the throughput of the windows is 120 in an hour, and the number of visits, 6. So we have that the throughput of the system is 20 cars per hour. And now we can use it here. So the number of visits of the robot that puts the door, 4 doors, multiplied by the throughput of the system that we have computed here, we get that the throughput of the robot that puts the doors is 80 doors per hour. Last law, and we will have a break. Okay? So far we have seen 4. This is the 5th. We have seen the utilization, the service demand, littles, and forced flow. And this is interactive response time law. It's based on the littles law for interactive systems. Which were interactive systems? The network with close. So when it finishes, it will start again after a delay. So there is the user interacts with the system does something, and then the user uses the output and works before doing another request. Why it is different from the little law? Why we need to tune something? Using the little law, we can compute the number of users in the whole system, and we have a population, so it's easy to know. The throughput, which rate they are being produced, are being complete, the jobs, and we can compute the R, the response time, residence time, cycle time. But it would be the cycle time of all the block. But for our computing system, we are not interested on the time of everything, only how much time it takes the system to answer. So the think time, we are not interested on that. So that's why this think time is called, this delay is called Z. So we will subtract. 2 ways of seeing this. The little law say that it was the number of users was the throughput times the residence time. Can move the residence time, so this time is equal to the number of users divided by the throughput. And this is true, so Litter's law applies, but in this case, the R we are computing comprises everything, also the think time, and we don't want to, when we want to know the response time of our system, we don't want to consider this think time. So we subtract the Z. Another way of seeing this is like what we called before the R, the residence time in the Litter's law. Now we are going to separate this. So it will be R plus Z. The R in which we are interested is this one, and we also have the Z. So we will have like the N. So this R and this R are different concepts. This is the R of the Litter's law for the residence time in all the system, and this R is our response time, the R in which we are interested. So only the part of the system. So we could say that then the number of users is equal to the throughput multiplied by this RS plus Z. And so we derive the same. Okay? We have this system which is quite similar to the one we saw on Wednesday. So the same Mu and a web server that processes 10 per second, an application server that processes 2 per second, and there are 2 resources, and a database that processes 2.5. So service time 400 milliseconds. We have a population of 400 users in our company, and the delay is 200 seconds. So they work, they create a document, they send it to the system, and when the system answers, they continue working another document in an average 200 seconds, and they will interact with the system. We have observed this system, and we have seen that there are 7,092 requests during an hour that were completed. Can you compute the system response time? Maybe? 2 seconds. Well, it's 3 and something, but let's use the formula. Interactive system. So we have user think time, and it's a closed workload. So we want to compute the response time. We know the number of users, 400. We know the throughput. It is 7,092 in an hour. So this is the throughput per second. So 3,600 seconds in an hour. This is 1.9702. Minus. So this is the same. The think time, which are 200 seconds. This part, so 400 divided by 1.9702 is 203.04. This would be the response time applying only the liters law. So every 203 seconds, we do a complete cycle. So waiting and using the system. So we subtract the amount of time we are thinking, we get 3. Seconds. So in average, users are waiting the response time of the system 3.04. We can have a break now. 10 minutes. Yeah. 10 minutes.
Do you remember?
No,
I don't know.
you are live on YouTube.
Spanish we use like we write.
Not the right moment to talk about this.
We start. This is subject.
This one, no?
Oh yeah. This is yeah. Okay. Or
Hello?
some other people will do trees like subject, verb, and this part of is another part of the phrase, and this makes
So let's start the second part
like
of the lesson.
makes thing like
So we continue with the exercises using the operational laws. People online already? Yeah.
yes, they say.
Okay. So we finished the previous lesson, the previous hour, computing the system response time using the last law we saw, the interactive response time. Now we are going to complete this exercise with more questions, and we will do one or two more exercises using all the laws we have seen. This is the kind of exercise you will find in the assignment as well. So, next question on this system. What is the resource that is closest to saturate? So we should compute the utilization for each resource. So we use the forced flow law to compute the throughput of each resource. We know the throughput of the system, 7,082 in an hour, and we will compute the throughput of each resource. Since this is direct, is 111, the throughput of each system will be the same, because the number of visits is 1. Will be the same of the throughput of the system. So the throughput of the web server is the same as the throughput of the application server, and the same of the throughput of the database, which is the throughput of the system times 1. 1 visit each. So we know also the service times, because we have the mu. So 1 divided by 10, 1 divided by 2, 1 divided by 2.5. And we know that there are 2 servers of the application server. See. So the utilization law tells us that the utilization of server is equal to the throughput of that server multiplied by the service time. So we multiply the throughput times 0.1, and we get that this web server is used around 20% of time, 0.19. The application server, multiply the throughput times the service time, and here we divide by the number of resources, as we saw in the first law. And this is around 50%, 0.99, the utilization of this server. And the database, the throughput of the database times the service time. It should be 0.4 here. Should be 0.4, the service time. So the inverse of the frequency. So let's assume that this 0.4 and the result is 0.7. So what is the closest to saturate? The one that the utilization is higher. So the highest number between 0.19, 0.45, and 0.78. So the one that is closest to saturate is the database. So if we have more users in the system, the first resource we should take care to scale it or change the implementation will be the database, will be the bottleneck. What is the percentage of time that users spend waiting? So the manager of the company, like users here producing the documents, and then they want them to send to the system, but they don't. The manager doesn't want the users to be waiting a lot of time without producing, just waiting for the answer of the system. So during their work day, how much time they spend waiting? Okay. So people online, today we had a peaceful first hour, but now we don't know how it will evolve. So percentage of time that users are wasting from the viewpoint of the manager. We saw that the cycle time was 203.04. And of these 203, they are waiting 3.04. So the proportion is 1.5% time. The users spend waiting for the system to answer, and 98.5 they are working on their documents. If we have infinite users, what is the maximum throughput we can our system will support? Let's think when we get utilization 1 of a resource. When it is saturated, it's the maximum throughput. Every time will be busy. Doesn't have any idle time. Of a resource, the throughput of a resource, okay. The service time of the resource, utilization low. So when it is saturated, the utilization will be 1. I'm working all the time. This is I have infinite users, so never idle. We know the service. So the maximum throughput that each resource can support is the service that multiplied by this throughput that makes 1. Cannot make more. So and we have the service time, which is 1 divided by this mu. And we have to multiply this by some value to make it 1. So we have that our first server can process 10 per second, so its maximum throughput will be 10 per second. Because when it is producing 10 per second, it is saturated. Even if I have infinite work to do, I cannot do more than 10 per second. Yeah. I can do less if there is no work to do at some point. So I'm idle. But with infinite users, I'm never idle. This one produces 2 per second, and we have 2 resources. So the maximum production, to make it be saturated, 2 times 2. 4. We cannot produce more than 4 per second. Sorry, for this one, we are using the utilization low, and when we have more than 1 resource, you saw that it was divided by the number of resources. So we have to use all the three variables. And for the database, I can produce 2.5 pairs each second. So my service time, my service frequency, 2.5 per second. So if I'm busy every time to make my utilization 1, is when I'm producing 2.5 per second. So the lowest throughput, this can produce 10, this can produce 4, and this only 2.5. So this is the maximum throughput of the system, because all of them are visited once. So if we had here some other visits, like, okay, you are producing this, but you are getting more visits for each production of the system. So now the database is our bottleneck, what will give the maximum throughput of our system if we increase the number of users. So if we add another resource to the database, which will be the maximum throughput? This is the previous one, so you can build on this. So if we have two databases, here we are in the database, we would be dividing by 2 as well. So to make the utilization 1, we would need double throughput. So instead of 2.5, we could serve 5. So then we get the minimum between 10, 4, and 5, and it would be 4. So if we add another database, then the bottleneck will change. If we have infinite users, so if the amount of users in our company increases, and we have already replicated the database, the next time we need to increment our infrastructure will be the application server, because it will be the next one to saturate. Another exercise. We want to compute the average system response time of an interactive system with these characteristics. "25 users, 18 seconds of average think time, 20 visits of a device for each job execution. We have seen that this device is used, the utilization is 30%, and 25 milliseconds of service time for each visit. If I do like this, first we create the model. Any volunteer to draw the model, like a queuing network? You can draw there in this whiteboard that is out of the camera, and I will draw. No volunteers? Okay. Interactive system. So there will be some users here, and then the system will do something, and they tell us that they are 25, and they think this delay is 18. And then they produce visits to a device which has 25 milliseconds of service time, so let's see, of 40. The inverse, 40 per second. It is used 30% of time with this, and before leaving, it revisits, actually 20 visits. In average. And we want to know the response time. So this is the same model.
Where did you get 40 from? Milliseconds 40? Where did you?
The milliseconds were 25. Service time. SK. Service rate, the inverse. So we can compute 40 per second.
I don't follow.
40 per second, actually. Sorry. The frequency. So if a request needs 25 milliseconds, 40 times 25 makes a second. So we can process 40 in a second.
Yeah.
Like just forcing you to think in both sense, like service time and service rate.
Yeah.
So we could say that the 1 divided by the service time is 25 milliseconds, or the move is 20 seconds to minus 1. 20 requests per second. So it seems that we can use the interactive response time low here. Some forced flow low, and utilizations, because we have there this is used the 30%, and so far we are not using this. So it seems that the response time will be that, what we want to compute, and divided by the throughput minus the think time. And so far we know that n is 25 divided by something, and the think time is 18. So we have to compute the throughput of the system. The utilization law told us that the utilization of a service center is the throughput of the service center times the service time. Now we know the utilization, they told us 30%, and they told us the service time, the 25 milliseconds. So it seems that we can compute this, utilization law. Then we have also the forced flow law that tell us that the throughput of a device is equal to the number of visits to this device multiplied by the throughput of the system. So it seems that we have here 0.3, the utilization, 25 milliseconds, so we can compute this. We use it here, and we have the number of visits, which were 20 visits, the definition. So we have this and we have this, so we can compute the throughput of the system, which is the only value that were remaining here. Okay? So this is 0.3 is equal to the throughput divided by the service time, 25 milliseconds. So 0.3 divided by 0.025. This is 12, maybe? Yeah. 12. So the throughput of this service center. Then we can use the 12 is equal, so we move this 20 dividing, 12 divided by 20 is equal to 0.6, which is the X, the throughput of the system. Here we can say 0.6. 25 divided by 0.6 minus 18 is 23.7. This is the response time of our system. So we have used the rules for the laws: interactive response time, utilization law, because we knew the utilization and we knew the service time, and we could compute the throughput, and the forced flow. When we knew the throughput of this resource, and we knew the number of visits, we could compute the number of the system throughput, which was the only remaining parameter in our formula of the interactive response time. Here it is, the solution. Next. Company uses a client-server application for the management of its resources. Can read in the meantime. There are two tiers. The first tier has two web servers that they share the workload evenly. The second tier has two application servers that provide complementary functionalities, and both should execute. And two databases that share the workload. Describe the system with an open queuing network. I can start, and then you will help me. The first tier includes two web servers that share the workload. Open network, there will be two web servers. Web server 1, web server 2. Then the second tier includes two application servers. So we don't know if there is one or more requests actually, so let's put it like this. Two application servers, and both should be visited. So now they are not in parallel, like one or the other, but they are in sequence. The application server 1, and then both have to execute the application server 2. We could have done the first application server 2 and then the 1. And we don't know if they repeat. And finally, it goes to two databases that share the workload. And this is like yeah. The parts, database, data server 1. Data server 2. Here we have our model. Arrivals, departures. We have observed the system 30 minutes. And we have seen that 450 requests completed. The service time of the web servers is the same for both of them, 0.1 seconds. The service time of the first application server, 0.15. The service time of the second application server, 0.2. The service time of the data server, both data servers have the same service time, 0.25. And we have also seen the demand.
They share the workload.
Yeah.
Yeah, does that mean that one job goes here, one job goes here?
Yeah, this is the routing. So when it comes here, depending on the routing policy, maybe probabilistic, with a probability here and another probability here, and it will decide randomly following this probability, or round robin, first one, then the other, then the previous one, then the, or join the shortest queue. These were the three kinds of policies we saw on Wednesday. When you join the shortest queue means that when the job is leaving this point, task, how many jobs do you have in queue, how many jobs do you have in queue, and I will join the shortest, because I'm expected to finish before. And we have also seen the demand. So the service demand of web servers were the same and 0.2 seconds. And their service time were 0.1. So what does it mean now? That if an execution requires 0.2 of this, but one execution of this only gets 0.1, that it will execute 2 times. So the number of re-entries there will be 2 times. I don't want to specify it in any way so far. I will do it during the next lesson. But the job will execute twice. So 0.1 plus 0.1. The service demand of the application server, 0.75, while their service time was 0.15. Means that it will execute 5 times. 0.75 divided by 0.15. The service demand of the application server, 1.7. And the service demand of the data, each of the data servers, 1 second. Okay, define the system model, we have done it. Compute, system throughput. $30 minutes, and there were 400 and something. 450. So this is not allowed. This is one of the first equations we saw. The throughput is the amount of requests we have seen finishing divided by the amount of time. So throughput, 450. We want by second, 30 minutes time 60. And this is 0.25. So a request every 4 seconds, 0.25 requests per second. $1,800 is the amount of seconds in 30 minutes, so 30 times 60. The visit number for each service center, so using the demand and the service time. We had the service demand law, which was the demand of a resource if the number of visits of the resource multiplied by the service time of the resource. The second law we saw. We know the demand of every resource and we know the service time. So we know because it was in the definition. So service time and in the other words, the demand. So for the application servers, it was, so this was it. The demand divided the service time is equal to the number of visits. For the first one, this was 0.2 divided by 0.1. So the number of visits were 2. The other was, this one was 0.75 the demand divided by 0.15. So it's 5 visits. This one was 1.7 divided by 0.2, so 8.5 visits. One thing that I have not said, but the number of visits is not an integer, so it can be a fractional number, and it may be below 1, as your first question about what happens if I go in one path or in the other. So if our system, I don't know if this is evident, but I didn't say it explicitly. If our system does like this, the number of visits will be less than 1. So we don't know if it is with probabilities. The number of visits will be equal to the probability of each path. If it is round robin, it will be half and half. So 0.5 visits, 0.5. And if it is joint sorted queue, it depends on the speed with which it processes. So, but in every case, the number of visits, the mean number of visits will be a number between 0 and 1. So it is not an integer, and it is not always higher than 1. It is higher than 0. Okay, and the last one was the service time is 0.25 and the service demand was 1. So the number of visits, 4. Two, 5, 8.5, and 4. Utilization of all servers. We have the utilization law. But here I'm using the service demand, actually, low. The alternative of the service demand, we saw 2 laws for the service demand. This was the first, and then the demand was equal to the utilization. So this is U, not B, divided by the system throughput. We know all of this, so we know the demand because it's on the 0.2. It's the statement of the problem, and we know the throughput because we calculated it before. So the throughput was the 450 divided by 1,800. So we can compute the utilization. The web server, it comes that the web servers are used 5%, 0.05. So we are using the service demand law. Even if there are different visits for the service demand, we use the system throughput. And the system throughput is the same for all, was the 0.25. And we multiply by the demand of each one, and so the web servers are, the utilization is 5%, the first application server 18%, the second 42%, and the databases are 25% used. And now we calculate the throughput of all servers. And now we have enough data already computed to use any of 2 laws. We can use the utilization law or the forced flow. What I not do. If we use the utilization law, we are going to get that the utilization of each resource is equal to the throughput of that resource times the service time. So it means that we want to compute the throughput of each resource equal as the utilization of the resource divided by the service time. We have there the results of the utilization, and the service times are given in the problem statement, which were the 0.1, 0.2, 0.25, and 0.15 was for this. So throughput, I'm going to use the red one, so I don't write the formula for each one, but I write on the, this would be 0.05 divided by 0.1, so this, the throughput, 0.5, of this would be 1.25, which comes from 0.18 divided by 0.15. This one will be 2.125, which comes from the utilization 0.425 divided by the service 0.2. So you see that, so it has more visits. And the last one is the utilization is 0.25 and the service time was 0.25. So the throughput of this is 1. Using the utilization law. Now we are going to use the forced flow to get the same result. This was the throughput of element of the system, a component of the system is the number of visits times the throughput of the system. We had compute before the number of visits, is this 2, this one was 5, 0.75 divided by 0.15, 5, 8.5 and 4. And we have the system throughput. It was the 0.25 that we are using there, and it came from the 450. So number of visits, 2 times 0.25, we get the 0.5. So both rules are giving the same answer, which is expected and good to get. The next one, 5 times 0.25, 1.25, which is the same as this. The application server 2, 8.5 visits times the system throughput, 0.25. It's divided by 4, so it's 2, 5 divided by 4. Yeah. 1, 2, and an 8. So the same as this. And for the databases, number of visits are 4, and the system throughput 0.25, so this is 1, which is the same as we obtained it from the other path. So they are coherent, and with this we finish today. So you will get one exercise like this in the assignment, and more things that we will, of what we will see next week.
Is it possible to put the slides on my Moodle?
Yes, of course, of course. I put the Wednesday ones. I put them yesterday afternoon. So I hope to put them, these ones, either this afternoon or during the weekend. So by Monday it should be there.
Is it possible to put next one as well, so that we can before the lecture, so we read it and prepare. We come here prepared.
The next, for the next lesson, I'm going to use a tool called JMT, Java Modeling Tools. So if you download and you learn how to use it, will be fine. But I don't have here the slide to show you. This one. So I will use this. That is a tool that with which you can model the queuing networks, and I will use this to evaluate the performance from the queuing network instead of operational. I will write it in my Moodle as well. If you So in the assignment there will be some exercises for operational lows. So even if you don't have a tool, you can still say something about the performance of the system using the operational lows, and some exercise about solving queuing networks, but using a tool. And I will use this tool. If you have any other favorite tool, you are free to use it.